I'm Antonio Sala, and in this video we are going to discuss a numerical example of the feedback linearization methodology. We'll do it by hand, even if of course Matlab can indeed help us with the symbolic math toolbox to carry out the required derivatives and algebraic manipulations. But doing it by hand at least once will help us better understand what we are doing. This will be the process we wish to control. In blue we have the state equation, and in green we have the output equation. The two outputs here will be the controlled variables, and u1 and u2 will be two inputs, manipulated variables, used to control y1 and y2. How does this methodology work? Well, first we need to take time derivatives of the outputs. So let's start with the first one, and as y1 is the first state, x1, then of course the derivative of the first output is just the first state equation. Here we have it. Now let's go with the second output. In this case, we need to apply chain rule, in the sense that y2 is a function of time, even if we did not explicitly incorporate it here in the notation for notational brevity and cleanliness. But indeed, y2, function of time, is a function of time to the third power plus another function of time. So, if we take time derivatives, we will need to apply chain rule, at least in the cube stuff. So we'll have sort of this thing. And in general, as y2 is a function of two variables which themselves are functions of time, the multivariable chain rule tells me that I will need to write this time derivative as the partial with respect to the first variable multiplied by the time derivative of x1 plus the partial with respect to the second variable multiplied by the time derivative of the second one. This abstract stuff ends up being this thing. So we will write this as 3x1 squared. We will, again, clean notation, avoiding to write t everywhere. 3x1 squared times this derivative of x1 plus this partial derivative is 1, of course. So I need just to copy the second state equation, and here we have the time derivative of the second controlled variable. Good. As we already have the inputs here, we need not taking any further derivatives. In, say, dynamic control of robots, we usually need to take two derivatives if our controlled variables are positions, but our manipulated variables are accelerations and torques. But in here, it's a simplistic example, and manipulated variables appear just by taking a single time derivative. Good. So we completed the first step of the procedure. Then, copying this and cleaning up a bit, we have this, and I highlighted in red the manipulated inputs. So now feedback linearization continues by assuming the following. First, forgetting about these derivatives and thinking only in the following algebraic equations, in which two arbitrary variables, v1 and v2, have been introduced. The meaning in a control context will be clear later. Now we simply say, imagine that we can equate the derivative of y1, i.e. this expression, to some artificial dummy variable v1, and imagine that the second expression can be equated to v2. Then we ask ourselves the question on whether we can solve for u1 and u2 so that these two equalities do hold. In order to check whether we can solve for u1 and u2, we need to have a look at the matrix that multiplies the inputs at the left-hand side, because the equations can be expressed in this way. So if this matrix is invertible, then we will be able to solve for u1 and u2 given v1, v2, x1, x2. And in fact, in a general setting, the values of the state that render this matrix non-invertible, I mean the values of the state that make the determinant of this matrix equal to 0, these points are called singularities. And in here, for instance, we have no singularity, but in a robotic application in which I wish to move my finger, then now I can move it up, down, left, right. But if I fully extend my finger, then I can move left, right, but up, down movement is impossible. So that's a singularity. But in this easy example, we have no singularities, so there are no regions of the state space that need to be avoided in my trajectories. So good. The thing is that this matrix in cyan is invertible, so we can solve for u1 and u2, and of course it's just moving this some stuff to the right hand side, changing sign and multiplying by the inverse of this matrix in a generic setting as I would do in Matlab. But well, in this case it's easy doing it by hand, so we will write the end result saying that if these things go to the other side changing sign, we get this equation for u1, and of course if I replace in the second equation that value of u1, then I get this expression for u2. You can just pause the video and check it yourself. So now we have finished the second stage of the feedback linearization methodology. First stage is take derivatives of the controlled variables until inputs appear, and second stage is introduce arbitrary values v1, v2 and solve for the manipulated inputs. So we finished that second stage, and then now it's almost done, in the sense that now it's the time to recall that if I replace u1 and u2 with these expressions, then the derivative of the first control variable will be v1, and the derivative of the second control variable will be v2. So what all these derivations tell me is that if I have my process with the state equations and output equations we started with, being these the control variables, and I program these equations, how? Well, inserting some code that from v1, v2 computes u1, u2, but of course in this code we need also the values of x1, x2. That's important because I need to fetch them from the process. So this is why these operations are called feedback linearization, because in order to compute this, I need to know the state, either because I measure it or because I have some sensors that allow me to compute x1 and x2 using the model. For instance, if I had sensors of the controlled outputs, then first state will be directly the first sensor, and second state will be this expression regarding the measurements. So, irrespective of the technology I use to obtain x1 and x2 from measurements, the fact is that they are needed in this block in order to implement this code. But once that code gets implemented, then if we just look from outside, what we get is that we have a black box in which these artificial variables v1 and v2 enter, and some code and some physics get executed. This is executed by my computer, this is executed by nature, but at the end, if v1 is the derivative of y1, and so with the second output, it means that the transfer function between this artificial input and output y1 is an integrator. y1 is the integral of v1, y2 is the integral of v2. So this is the apparent transfer function that all this code and physics end up having if we look at it from this artificial v1, v2. So this is why this block is called a feedback linearizer plus decoupler. Feedback because we need x1 and x2, so this is a state feedback somehow, and linearizer because what we can see from the outside seems linear, even if there are very complicated nonlinear expression insides, but apparently it's linear, and decoupled. You can see that v1 only seems to have an effect over y1, and v2 only has an effect on y2. So the thing is that, of course, once we have this linear decoupled system, feedback linearization finishes by programming these equations, and then let's say this first order system will be controlled with, say, a proportional controller, or we might wish to add integral action to cancel low frequency disturbances or modeling errors. But of course, designing this PI is much easier than designing a nonlinear controller for the original process. So that's the advantage of the approach. We'll summarize and conclude here. In this video, we have a nonlinear plant, which at first glance would need nonlinear control. But in some cases, the feedback linearization trick does work because we are lucky with these derivatives, inputs, whatever. And then by programming some equations into this feedback linearizer plus decouplers, of course we need state feedback, then programming these equations, we can transform the system to be apparently a diagonal transfer function matrix containing only integrators in the diagonal. So if this works, then subsequent control design can be easy because it's linear and decoupled. This may not always work. We may have singularities. We may not be able to access the whole state with reliable sensors. So this is not the holy grail for nonlinear control, but when it works, it's an exact linearization that allows trajectory tracking with linear controllers on top of it that behaves better than the approximate linearization with the partial derivatives and the increments around the constant operating point, which is approximate. And of course, the constant operating point is not intended to be used in trajectory tracking. So we finish with this. Thanks for watching.